Hi, I'm Brian Freer, tutoring high school physics. Today's topic, pendulums. So pendulums are very similar to springs in that they go through something that looks a lot like simple harmonic motion. You take a pendulum, you pull it out, and it'll swing back and forth and back and forth. It even has a restoring force, which we can describe as mass times gravity times sine of theta. Yes, a component of the force of gravity is the restoring force. So let me show that to you. Here I have a pendulum that is out swinging, and here's the force of gravity going downward. Well, if we split up into components, we find that one component is going to oppose the force of tension in the string, so that the pendulum doesn't just fly off the end, and the other component is pointing right down into the equilibrium position. Once it swings past the equilibrium position, it'll start pointing back this way. So we can actually find the restoring force on this particular pendulum. So we have mass of 5 kilograms times an acceleration due to gravity 10 meters per second squared times the sine of theta. So this theta is 45 degrees here. You just need to move this one over here, and that's perfectly okay. Geometry. Anyway, so moving right along, 5 times 10 is going to be 50 newtons times the sine of theta. Sine of 45 degrees is square root of 2 over 2, so we get 50 times square root of 2 over 2 newtons, or 25 square root of 2 newtons. The trouble with pendulums, however, is that they don't actually undergo simple harmonic motion. In order for that to happen, they would have to have a restoring force that is proportional to the distance from their equilibrium position. In this case, it would have to be proportional to theta, measured in radians as opposed to degrees. This is not true. It's actually proportional to the sine of theta. However, for very small theta, sine of theta is about equal to theta. So our restoring force equation becomes F equals mg theta. This is a simple harmonic motion. So then we can start using these equations to find the frequency and also the period of our particular pendulum. Remember, you'll only need to memorize one of these because 1 over the period is equivalent to the frequency, and 1 over the frequency is equivalent to the period. Okay, so let's solve for the period and frequency of this particular pendulum. So, period equals 2 pi times the square root of the length of the string over the acceleration due to gravity. We have a length of 5 meters and acceleration of 10 meters per second squared. And we have 2 pi times square root of 5 over 10 is 1/2, and meters divided by meters per second squared is just seconds squared. So then we get 2 pi over the square root of 2 seconds. Alright, we need to not have radicals in the denominator, so we get 2 pi times square root of 2 over 2 seconds, which is just going to be pi times square root of 2 seconds. So that's going to be our period. To find our frequency, we simply invert that, and we have our frequency as 1 over pi times square root of 2 seconds. I just got the radical out of the denominator. So we have square root of 2 over pi square root of 2, sorry, not square root of 2, 2 seconds. To recap, pendulums almost undergo simple harmonic motion. To find the restoring force of the pendulum, you multiply the mass times gravity times the sine of theta. For a very small theta, you can consider pendulums to actually undergo simple harmonic motion, and therefore you can calculate the period and the frequency of the pendulum. The period is equivalent to 2 pi times the square root of length of the pendulum string divided by the acceleration due to gravity. The frequency is equivalent to 1 over 2 pi times the square root of the acceleration due to gravity divided by the length of the string. But you only need to memorize one of those equations because you can simply invert your answer to get the other. Alright, that's all for now. Again, I'm Brian Freer. See you next time.